Hi everyone, welcome back. Today we'll be talking about the shell method, which is another method of determining three-dimensional volume when a two-dimensional surface is revolved around a specific axis. We'll see it's very similar in computational levels to the disk and washer methods from last video. The main distinction here is that instead of looking at washers, which we draw like this, for instance, where we look at a horizontal strip if we're working around the y-axis, and we draw out this inner circle, this outer circle, and we say that it has a little bit of depth to it. So we give it a small dy depth, take the volume of that, we move up a little dy and do the same thing. But the main distinction here is that we are indeed working with strips that are drawn perpendicular to the axis of revolution. And these strips form washers when you go ahead and revolve everything around. With the shell method, instead, what we're going to be doing is we're going to be working with strips that are actually parallel to the axis of revolution. So I'm going to draw my little strip here, and when I revolve this around the y-axis, I end up drawing this like cylinder-looking shape, obviously called a shell. And the reason it's called a shell is because we give it a little tiny bit of width to it to give it a volume, right? So we call this little width dx that we give it. And when we trace it out, it forms like a hollow shell, like a Pringles can almost without a bottom. And then if you want to do it again, you move over to the right a little bit, draw it again, and do another strip. This diagram's terrible, but there are a lot of good ones online illustrating exactly how this works. Of course, you're going to get the same volume doing it either way, so this video is mainly trying to help you figure out exactly which method to use, and if it's more difficult to use one or the other. Essentially, the main distinction comes down to which variable you're going to integrate with respect to. So if you notice over here with the washer method, if we wanted to revolve around the y-axis, what you end up doing is you do an integral of pi times a big radius squared minus a little radius squared, those being the distances to the outer edge and the inner edge respectively. But notice we're going up, so this is a dy integral, which means everything needs to be in terms of y. Over on the shell method, on the other hand, I'm tracing out these cylinders. These cylinders essentially have a volume of its surface area times dx. So the surface area of a cylinder is its circumference, which is equal to 2 pi times the radius of that shell, the radius being the distance from the axis of revolution to our shell that we're drawing. And then to complete the surface area, we also add the height of the shell, which is obviously just the height of the strip that we drew. And then what we said is to give it a little bit of volume, we're going to add a dx element to it. And so notice we're going to be integrating with respect to x. Everything will be in x. So kind of it comes down to, do you want to be working in y or do you want to be working in x? Are your functions given in an easier way to work with in one variable versus the other? But the computations are going to be about the similar amount of difficulty. So let's go ahead and get started with an example. Let's look at example A, where we have the line y equals x and the line y equals minus x over 2. And what we're doing is we're revolving that around the y-axis. So let's go ahead and use the washer method first, as we're used to, because you don't like the shell method, it's new, whatever. So we run into an issue almost immediately. So if I try to draw a strip, which I'll be doing it perpendicular to the axis of revolution, right? I can easily find my outer radius here. It's going to be 2, and that is x is equal to 2. My inner radius is going to be to that function when x is equal to y. And that's fine and dandy until you get down here at the origin. So I can do this at all of these points, but the second I flip into negative y values, I have a different function. So my little r changes. And that's not really the end of the world, right? So we can set this up anyway. My big R down here, I'll put it down here. My big R down here will be 2 as well, but my little r now will only go to x is equal to minus 2y. So what we have to do then is we have to split this up into two integrals, one that deals with the volume here and one that deals with the volume here. That's not going to be too fun, so let's try the shell method instead. We know that's going to be 2 pi times a radius times a height times dx. And so our radius is going to be the distance from a vertical shell, right? So now I'm working this way to trace out the cylinder like this. It's the distance from the axis of revolution to that shell, which it sounds trivial to say, but it's actually just the value x. So x by definition is the distance from the origin, sorry, from the y-axis that your point x currently is. So that's a little weird to get used to, but it is just x. And then the height is going to be the difference between these two functions. I didn't draw this very well, sorry, it goes all the way down. So I end up with y is equal to x minus negative x over 2 dx. My bounds are going from 0, right? So I draw a vertical bar here, all the way up until x is equal to 2. So I draw the vertical bar over here. And I'm left with the integral of 2 pi. This simplifies down to positive 3/2 x, so I get 3/2 x squared from 0 to 2 dx. And on an exam, this is already looking better than splitting it up. Okay, so if you do this integral out, I got 8 pi thirds. And yeah, so that's the shell method here. Let's take a look at another one here, example B. Let's revolve this time around the x-axis, where it gets a little trickier. But let's take a look at the washer method, or let's do the shell method first, actually. So, we like the shell method on the last one. We think it's better, so let's take a look at it. If I'm revolving around the x-axis, my strip has to be drawn parallel to the x-axis, which means everything needs to be in terms of y. So my distance from the axis of revolution to my strip is going to simply be y. And then the difference between, the height of my strip is going to be the distance between these two functions here. So from here to here is going to be my height. And that's given simply by the difference between the two functions here, which is x is equal to 3 and x is equal to 3 minus y squared. And again, we're working vertically, right? So I'm drawing a strip here and here and here vertically. So I'm going from 0 up until the square root of 3, which is my top bound. This is dy. Okay, so this is nice. This cancels out quite nicely. You get 2 pi integral from 0 to root 3 of 3 minus 3 becomes 0. You get positive y squared, so it's y cubed dy, and you're in business. You can also try it with the washer method. You'll actually find it's simpler, but it takes a little bit more getting used to. Remember, if you change into the washer method, you're now drawing perpendicular to the axis, so you have to change this equation here to be y is equal to something. That's not always going to be fun. But yeah, if you finish this integral out, in case you want to check, I got 9 pi halves. It's good practice to try it with the washer method. All right, our last example here, we're going to do something a little funky, and we're going to revolve around a different axis than just the coordinate axes. So let's go around the line x is equal to 4. We have the shape, and I actually didn't write the function down, which is a problem. But it's just y is equal to root x here, and we have bounded on top by y equals 2, bounded on the left by the y-axis. Let's go ahead and do the shell method here. So again, we're going to be doing 2 pi, and then I need to draw my strip. If I'm going about the line x is equal to 4, I need my strip to be parallel to it, so it's going to look something like this. This is a little tricky, right? So we know our radius is by definition this distance here. This is the radius we're looking for. So it's not obvious. What I like to do is label all the distances I know. So I know this distance here, I'll do it in blue, I guess. This is by definition x, right? So at any given x, the distance away from the origin is x. This distance here, all the way from the origin to that line, is simply 4. And so you can take the big distance 4 and subtract off the small distance x, and you get the red line, which is our radius that we want, to be 4 minus x. So that's a good trick of figuring that out. It's also good to note that when x is equal to 4, you have the smallest radius, which is ideal, given this equation here. And then our height is simply going to be the difference between these two functions, which is 2 minus the square root of x dx. The last thing is our bounds. Of course, we have to draw the vertical line at every point, so we go from 0 to 4, and we're done. So here is actually not the easiest to do, right? But the point is you can FOIL this out, and you can do, essentially that integral. You have some 3/2 powers going on, but it's not terrible. If you came across that on an exam, you might want to just go ahead and do it if you're running out of time. But if you have some time, you can check out the washer method instead. So here we have pi times the integral of something that's big R squared minus little r squared. So my big R here is going to be, now, I know this is difficult because it's the same diagram, so I apologize, but it's working this direction here, perpendicular to the axis of revolution. My big R squared here is always going to be 4, because it's the distance from here all the way out. My little r is going to be constant as well. This time we have, let me be more specific here. This is x is equal to 4. Here, our little r goes from the axis of revolution to the inside point of this function, which is 4 minus that distance. So we have x is equal to 4 minus y squared. And then what you can do is you can square both of those. So you get 4 squared minus 4 minus y squared dy. You'll be going in the y direction this time from 0 to 2. You have a similar looking equation here. You'll get this 4 squared and that 4 squared to cancel out. And you'll just have a parabola, and y might be simpler, but it did take longer to set up. So, it's really up to you at this point as to which method you like to use. I suggest getting good at both of them, getting a lot of practice in, because sometimes you'll come across a scenario where you actually cannot do the integral. I didn't have a good method here to do it, but there are methods out there where you're forced into using either the shell or the washer, and you don't want to be at that point on an exam when you haven't studied the shell method in months. So I hope this was a good review.